Hello and welcome to this episode of Physical Attraction. This one on nuclear fusion is called A Sun of Our Own. Reporting science in the newspapers is very tricky to get right. There are many reasons for this. One is that we have a narrative of science as taking place in dramatic, revolutionary breakthroughs, and this of course is also what sells papers. The incremental, limited nature with which real science often advances, small progress on previous results here, an interesting experimental anomaly which needs to be peer-reviewed and potentially corrected there, is not often how we think about science, and it's certainly not what sells newspapers. At the same time, scientists who have to work on very specific problems, so specific that very rarely is it that anyone can even comprehend outside of the field what precisely they're working on, want to explain why their research is relevant and important. So you'll see 100 press releases a year in the scientific literature with a new breakthrough in renewable energy or carbon dioxide removal or quantum computing or some such sexy topic. And then there is always the temptation to sensationalise this discovery into the big one, the one that will change the world, and mention that the results are preliminary, or disagree with other results, in a footnote, if at all. Occasionally, a dishonest journalist will take a single result from a paper completely out of context. A colleague of mine here at Oxford probably remembers with irritation that, in a paper where the climate sensitivity to doubling carbon dioxide was estimated, the headline was 11 degrees Celsius, when this was actually the very upper limit that couldn't technically be ruled out, even though it was considered highly unlikely. I imagine for the scientists involved there are very mixed feelings. On the one hand, it must be nice to see enthusiasm and excitement about your work. On the other hand, there's suddenly an awful lot of pressure on you to be correct, and to live up to the hype that wasn't entirely whipped up by you. I imagine these are the mixed feelings that the scientists at Britain's Harwell Laboratory, working on the Zeta experiment, felt if they happened to catch a glimpse of the tabloid newspaper, The Daily Sketch, on January 25th, 1958. A sun of our own, and it's made in Britain, trumpeted the newspaper on its front page. Our scientists Sputnik the Russians, for peace. Meanwhile, the Daily Mail, accurate as ever, reported, the mighty Zeta provides limitless fuel for millions of years. And the newsreels were enthusiastic too.
Headlines for Harwell. Another spectacular triumph in nuclear research. This is Zeta, Z-E-T-A. Make special note of those initials, for they spell a British scientific achievement without parallel for the benefit of mankind.
The news from Harwell tonight is that British scientists have achieved a breakthrough towards perhaps the most glittering material prize in the history of mankind, the achievement of unlimited power from water.
In May 1957, Britain became the world's third hydrogen bomb nation with this detonation off Christmas Island, 1,200 miles south of Hawaii. Now, 8 months later, comes another headline announcement. Shown for the first time is the giant machine called Zeta.
From Harwell, one of the announcements of the century. This is apparatus Zeta. Mr. Pease on the left runs the physics side. Mr. Carruthers is the designer. Sir John Cochrane. It may be many years before this great British achievement reaches the power station stage. But here at Harwell, the first steps have been taken. And this handful of British scientists may have given mankind the key to all the power we shall ever need.
The press attention surrounding the Zeta experiment was, in fact, so intense that even the wife of one of the chief scientists was photographed for a pull-out spread in a newspaper and given the title Mrs. Zeta. And when you know that millions of people around the nation are reading over their morning toast, the mighty Zeta provides limitless fuel for millions of years, you're probably going to feel a little bit like maybe this whole thing is spiralling slightly out of control. When Juan Perón and Ronald Richter had caused the original fusion flurry, it had been quashed pretty quickly. No one had heard of these scientists. Very few people thought that Argentina, of all places, had been the first to crack fusion. It wasn't even widely agreed at the time that fusion would even be possible on Earth. But Zeta and Harwell were different. They were reputable. In fact, as you'll remember from previous episodes, the whole idea of pinch nuclear fusion had come from British scientists at Oxford, when James Tuck went over to the US and got funding for his perhaps-a-tron, and the pinch nuclear fusion research program that produced those all-important neutrons at Los Alamos. He'd got the idea from British scientists. Britain was the first country in the world to have an atomic weapons project, although it was very quickly dwarfed and outpaced by the Manhattan Project. It became clear after 1945 and the start of the Cold War that concerns about spies leaking classified nuclear secrets would mean that the US would not share their nuclear technology with Britain, and this put Britain at a distinct disadvantage. After one particularly demeaning phone call, the Foreign Secretary blustered into a meeting about developing the nuclear bomb and said, "We've got to have it, and it's got to have the bloody Union Jack on it." A few years later, sure enough, Britain's nuclear scientists had, more or less independently, developed nuclear weapons. On the day that those headlines about Zeta were published, scientists and journalists were crammed into the aircraft hangar at the Nuclear Research Laboratory. For several months, rumours and early experimental results had been leaking out of Harwell to the press, suggesting that they were on the verge of announcing a big breakthrough into fusion. At the press conference, the Director of Research, Sir John Cockcroft, described the process of nuclear fusion and said, quote, "Using Zeta, we have achieved temperatures of 5 million degrees for a few thousandths of a second." And Chief Scientist Sir George Thompson commented that yes, say it with me now, within 20 years it should be possible to have viable nuclear fusion reactors. Where did this come from? As we discussed, the British fusion efforts were focused on the pinch concept. Take plasma in a torus and then jam a huge current through it. That current will cause a magnetic force that pinches the plasma inwards, compressing it, hopefully, to fusion temperatures and densities. In the early 1950s, several prototype machines were built both in the US and the UK. But they quickly ran into instabilities, the dreaded kink and sausage instabilities, where tiny defects on the surface of the plasma would quickly spiral out of control, with the plasma bending, twisting, writhing like a snake and smashing into the walls of the torus. The issue was density gradients. When the pinch current was applied, any area of the gas that had a slightly higher density would create a slightly stronger magnetic field and collapse faster than the surrounding plasma. This caused the localized area to have higher density, which created an even stronger pinch, and a runaway reaction would follow. The quick collapse in a single area would cause the whole column to break up. The physics teams came up with various solutions to these instabilities. One idea was to increase the rate of compression, perhaps by passing a much larger current through the plasma much more quickly. That way, the compression would happen so fast that the plasma simply wouldn't have time to respond and react in its own self. The density gradients wouldn't then come into play, and the whole plasma would be compressed by a sudden shock wave. That's something closer to how things are done in a thermonuclear bomb, where, as we talked about before, there simply isn't enough time for the plasma to move around, for the fusion fuel to move around and react to the forces that are acting on it beyond just being compressed. This was sometimes called the fast pinch idea. Other concepts were more ingenious. For example, it started around this time that people would wrap the entire inside of the vacuum tube in a thin metal sheet. In electromagnetism, there's a famous phenomenon called Lenz's law. It relates to electromagnetic induction, that is, how magnetic fields can cause electrical currents. When a changing magnetic field is applied to a conductor, it induces an electrical current in that conductor. And this is the principle behind basically every nuclear power station. You change the magnetic field through some wire by spinning it around in magnetic field lines, or by spinning the magnet. This results in a changing magnetic field in the wire, and this in turn causes a current to flow. But the current itself has its own magnetic field. Every electrical current generates a magnetic field around it. Lenz's law tells us that this magnetic field has to oppose the changing one that's inducing the current. I think the easiest way to understand this is via conservation of energy. Imagine that you could move a magnet towards a coil of wire. The magnetic field in the wire changes as you do this, which causes a current to flow through the wire. If that current then produces a magnetic field that drags your magnet towards the wire, you're in trouble with conservation of energy. You could imagine moving a magnet a little way towards a wire, which would then generate a magnetic field that dragged the magnet in, and then it would just accelerate with no apparent source of energy towards the wire. And obviously we don't see this in nature, it just doesn't happen. This would be amazing for power plants, of course. They just have to set the magnet spinning, and the current would cause it to accelerate and spin forever, without having to burn any nasty fossil fuels, or design any complicated fusion reactors. But of course this isn't how the world works, otherwise we would have unlimited free energy. Instead, to produce the energy in the current that's induced in the wire, you need to act against the force, and of course, because really all you're doing is pushing the electrons along somehow. And the force is the tendency of the induced magnetic field, the induced current, to repel the magnet. Physicists working on the fusion reactor thought they might be able to exploit Lenz's law. Imagine the plasma as our magnet. As it moves towards the thin metal sheet, it induces a current in that metal sheet which opposes the motion of the plasma. So you can perhaps hope to stabilise a plasma this way, using Lenz's law in a conductor to push the plasma back. Basically what's happening here is, as the plasma moves towards the metal sheet, it's pulling in those metal sheet charges in a way that those charges then push the plasma back to where it belongs. So you hopefully have a more stable configuration. Sadly though, this approach seemed to work better for cancelling out large-scale movements, say the entire plasma column drifting to the left, and did little to calm these instabilities where a small region of plasma bursts out and destabilises the column. There was also a stabilised pinch concept, where additional magnets wrapped around the torus would hopefully act to damp and cancel out any instabilities that occurred when the pinch was applied. Zeta was an ambitious attempt to go one step further than earlier pinch experiments. Zeta stands for Zero Energy Thermonuclear Assembly. The zero energy refers to break-even, so the hope was that the nuclear fusion reactions would produce as much energy as was put into the machine, a small jump away from a power plant. It was the largest machine that the British had yet constructed, although it cost a relatively small amount, $1 million. Already the Model C Stellarator in the US, the next biggest fusion reactor, cost 20 times that. And it incorporated both types of stabilisation, the metal padding on the inside of the torus that was going to exploit Lenz's law to push the plasma back into place, and the additional magnets wrapped around the torus that would stabilise the pinch, along with an induction magnet that would allow them to jam 100,000 amps through the plasma when they switched it on. The initial results were very exciting, which was probably why rumblings got out to the press. The initial stability problems with the plasmas were much improved. The plasma lasted for milliseconds rather than microseconds. It might not sound impressive, but improving things by a factor of 1,000 is impressive. I wish that would happen to the listeners on the show, or maybe my bank balance. But most exciting of all were the neutrons. Every time the machine was switched on to blast a pulse of plasma around, there was a burst of around 1 million neutrons. Naturally, this looked exactly like nuclear fusion. At the same time, the physicists knew that there were perhaps other ways that neutrons could be produced in the intense conditions inside the reactor that might not be proof positive of thermonuclear fusion. Measuring the temperature of the plasma would prove critical. If the temperature was high enough for fusion, and a burst of neutrons was also being emitted, then fusion seemed to be the most likely culprit. If, however, the plasma wasn't being heated sufficiently, then the neutrons couldn't possibly come from large-scale fusion. But directly measuring the temperature of the plasma proved to be extremely difficult. Although Zeta actually had windows that allowed you to look at the plasma around the outside, you couldn't very well stick a thermometer that goes up to 5 million degrees Kelvin in it, because no such thing existed. Instead, they had to measure the temperature indirectly, using the light emitted by the plasma. The idea here is that the Doppler effect, the stretching and squishing of the wavelength of light as the sources that emit it move around, in the same way as sound waves are stretched and squished when an ambulance goes meow past you. This technique suggested that there was a 1 to 5 million Kelvin temperature in the plasma, hotter than anything that had been achieved before. Thus the leaks to the press and excitement arose. In the months leading up to the press conference and the famous headlines at the start, the British press published an average of 2 articles a week about the Zeta experiment, and the Americans got involved, sending scientists to inspect the Zeta machine. Here, the US-UK rivalry grew bitter, with some pundits suggesting that the US were delaying the release of results from the Zeta experiment because they couldn't yet reproduce them, and didn't want to admit that the British were scientifically ahead of them. The US certainly acted to delay the publication of results from Harwell, and there was a great deal of bitterness when they were eventually published in Nature in 1958, alongside results from American experiments. Here, the US-UK rivalry grew bitter, with some pundits suggesting that the US were delaying the release of results from the Zeta experiment because they couldn't reproduce them and didn't want to admit that the British were scientifically ahead of them. The US certainly did act to delay the publication of results from Harwell, and there was a great deal of bitterness when they were eventually published in Nature in 1958, alongside results from American experiments that had been conducted afterwards. Lyman Spitzer, with the Stellarator idea and the ski lift, was one of the American fusion scientists who had inspected the Zeta. While initially he thought they had cracked fusion reactions, he soon had his doubts. According to his calculations, the pulses of current simply weren't firing for long enough to truly heat the plasma to 5 million degrees, and if the plasma wasn't at fusion temperatures, the neutrons couldn't be from fusion. Nevertheless, at the famous press conference at Harwell when the results were announced, the director was quizzed about the neutrons. How sure was he that they had achieved nuclear fusion? The Harwell scientists had more or less agreed beforehand to say, these are preliminary results, further testing is needed before we can be sure, but Cockcroft went on the record as saying he was 90% certain that thermonuclear fusion was happening inside Zeta. And this, as much as anything else, fueled the press hype around the experiment. Cockcroft, after all, had won the Nobel Prize for nuclear physics research just 7 years ago. He had worked with Rutherford, the man who had discovered the nucleus. His Nobel-winning experiment was the first to artificially split an atom. He was no Ronald Richter, and as one of the most outstanding and respected British scientists, everyone had a reason to believe when he said it that Zeta had indeed cracked fusion. Soon enough there was talk of building a Zeta 2, which would aim to reach 100 million Kelvin and generate net power. Papers talked about unlimited power from seawater, no more smog, no more coal, no more oil. As part of the hype surrounding the device, universities around the world, including in Osaka in Japan and in the United States, began announcing their own versions of Zeta. Some, like American devices Columbus 2 and the Perhapsatron 3, were generating their own neutrons in due course. Even the government of the Soviet Union congratulated the British on their techniques and expressed their admiration, with a slight attempt to steal a little glory by pointing out that, of course, Sakharov had already come up with similar ideas. But not everyone was convinced. Spitzer was objecting on the grounds that the temperature reached couldn't possibly be high enough, and Basil Rose, who worked at Harwell, was not convinced that the neutrons were really from fusion. Fortunately, he was also the guy who was basically in charge of experiments with subatomic particles at Harwell. He was in charge of their synchrotron, a 1950s particle accelerator, much like a much smaller version of the LHC today. Back then, subatomic particle detection was a little less accurate, but a lot more fun. They used a cloud chamber, where you take advantage of supersaturated air. When particles like neutrons pass through a cloud chamber, they bash into atoms and ionize them, and those ions have an electrical charge, which attracts surrounding water droplets, causing a little cloudy trail to follow behind the path of the particle. By studying the tracks, like little contrails behind aeroplanes, you can figure out what your subatomic particle is, how quickly it's moving, and so on. I just found out that you can actually build these in your living room, and now I long for the day when I actually have a living room, so that I can make one. Maybe that would be a good bonus episode. Basil Rose suspected that the neutrons weren't being produced by thermonuclear fusion, and clearly measuring their properties would help to test this hypothesis. And this was where Zeta's triumph began to unravel. First, Basil noticed that the neutrons were very highly directional. Yet in the hot, colliding plasma, you'd expect neutrons produced by thermonuclear fusion to spread out in all directions. But the real killer was in an ingenious experiment. Run the current backwards through Zeta, with the current running in the opposite direction. If what you're really doing is compressing the plasma and producing neutrons through nuclear fusion reactions, the apparatus really shouldn't care about the direction that the current runs through the tube. But doing this totally changed the number of neutrons and their energy. Neutrons that were in the direction of the current had far more energy than those that were in the opposite direction to the current. Fusion reactions simply shouldn't explain that. And similar experiments at the Perhapsatron and the Columbus experiments showed that their neutrons also changed when you reversed the current. So it turns out that the neutrons were a result of another dreaded plasma instability. When little pinches, twists or kinks appear in the plasma, and we talked about how these density gradients can very quickly get very big, the electrical and magnetic fields grow and grow in the region of this instability because you have lots of charged particles close together, and this can result in very small regions with extremely high electrical fields. Those electrical fields can in turn accelerate nuclei in the direction of the pinch current. They then smash into the rest of the much colder plasma or the walls of the detector. This can knock neutrons out of the nuclei or out of the detector walls via a process called neutron spallation. You can even get lucky and see a small number of fusion reactions where the hot nuclei successfully smash into a colder one and fuse. But this is not at all how the machine was supposed to work. The incredibly hot nuclei that actually reached fusion temperatures were the product of an instability, and so you couldn't hope to sustain their production. They were a brief burst as the instability killed the plasma dead. The Zeta machine was supposed to uniformly heat the plasma, so all the nuclei were hot, and the hot nuclei could then fuse with each other. It was not supposed to create small numbers of ultra-hot nuclei that would bash into things, knock out neutrons, and maybe occasionally fuse. These reactions were not going to produce energy, and Zeta was inherently unstable. Rather than a sustained burn then, the plasma in such a device would flicker and snuff itself out. The result was deeply embarrassing for those that had worked on Zeta. Cockcroft himself tried to save face in publishing a retraction that said, It is doing exactly the job that we expected it would, and functioning exactly the way we hoped. But the damage, of course, had been done. Zeta did represent a step forwards. You can talk to the scientists involved in it now, as the BBC did for their excellent documentary, Britain's Sputnik, and you'll hear them, perhaps a little defensively, point out that it allowed us to advance our understanding of plasma physics at high temperatures. The real irony was that a few months later, another similar device called Scylla managed to achieve thermonuclear fusion using the pinch effect. This time they really did get up to temperatures of many millions of Kelvin, and they genuinely did produce neutrons from thermonuclear fusion. But the scientists were very cautious about announcing their results. There was no fanfare, and by the time in the 1960 that they finally said they were willing to stake their reputations on having achieved thermonuclear reactions, no one seemed to care all that much. The world's first controlled thermonuclear fusion experiment took place with the Scylla pinch device in 1958 at Los Alamos, following on from work by Zeta and the other pinch devices. But these days, very few people, myself included until I started researching this episode, have even heard of this experiment. There were of course geopolitical reasons that the Zeta hype got out of control. For a start, you have to remember where Britain was in 1958. From a vast empire that ran a quarter of the world, they had been reduced by the First and Second World Wars to a second-rate power. The Suez Crisis in 1956 had been a national embarrassment that had demonstrated the British were subordinate to the Americans. It was clear that the empire was in decline, and the global power dynamics were going to be about a competition between the US and its allies and the Soviet bloc. But Britain could still be a major player on the world stage scientifically. Sputnik was in that headline for a reason. Just the year before, the Soviets had succeeded in launching the Sputnik satellite into Earth's orbit. So the breakthroughs at Zeta gave the British politicians and press something to trumpet, at a time when they felt it was needed. Concern over the leaking of nuclear secrets meant that the international fusion efforts were just not collaborating with each other. In fact, Klaus Fuchs, who loyal listeners will remember we discussed as the Soviet spy who leaked nuclear secrets to the USSR, way back when I interviewed Simon Ings about Stalin and the scientists, was head of theoretical physics at Harwell, where he was particularly sceptical of nuclear fusion as a power source. When it was discovered in 1950 that he had passed secrets to the USSR, fusion research became highly classified. This meant that no one's fusion research program was transparent. It was impossible to tell if someone else had made the breakthrough first. Nowadays, most fusion research is done fairly out in the open, and arguably the furthest along projects are these huge collaborative efforts like ITER. But the secrecy spurred competition, as Joan Lisa Bromberg describes. She wrote, quote, "Secrecy prevented the scientists of Project Sherwood from forming a realistic picture of the state of the art for fusion science and technology on a global scale. For all they knew, the Soviets were already mass-producing desk-sized reactors. Yet this secrecy also set the project back by years, if not decades." Tuck and the pinch team at Los Alamos ended up finding more or less the exact same problem that Zeta had. If they had communicated with each other, perhaps Zeta would have done some more tests before holding a press conference, and the result would have been far less disillusionment about the nature of nuclear fusion. Those are all counterfactuals for another day, though. After the embarrassment and apparent failure of Zeta, all that hype came crashing down. Fusion scientists realised that a sustained reaction was simply not going to be another few years in a slightly bigger machine away, that this was going to be a very complicated, stop-start endeavour that would take years, if not decades, to really achieve anything in. Progress was being made. Confinement times were being increased. They were getting closer to the kind of conditions where fusion reactions might work out. But every step forward seemed to run into new false hope, a new instability, another cause of inflated expectations followed by disappointment. The dream of easy, unlimited power from fusion was slowly slipping away. Funding was starting to dry up. There's only so many times that you can hear that the next big machine, or the next one that happens to cost 10 times more, will be the one that successfully delivers on the inflated expectations from the media and the headlines. And in many ways, the whole field of physics, particularly nuclear physics, was falling from this peak of inflated expectations. In 1945, there was every reason to believe that physicists were on the verge of fully understanding the world, taming the forces of nature, and changing human society into a kind of sci-fi utopia with limitless energy to perform all of our desires. But as the decades wore on, the promises seemed more and more likely to be unfulfilled. Just as the shadow of the nuclear bomb hung over the world after the Trinity test, so the shadow of the experiments like Zeta, perhaps unfairly considered failures, would hang over the nuclear fusion community. This was not going to be easy. And yet, even as the fusion scientists were licking their wounds, there were 2 new developments taking place that would give rise to totally new kinds of devices. Devices that would revolutionise the field of fusion. One would create a new sort of fusion device that could achieve vastly improved performance and is still the leading candidate to this day for nuclear fusion. And the other would create an entirely new way of attempting to achieve fusion. It's there, with these developments, that we'll pick up the story next episode. The archive radio footage you heard earlier was from Britain Sputnik, a 2008 radio show about the Harwell Zeta experiment, and you've been listening to Physical Attraction. You can find us online at www.physicspodcast.com, where you'll find the contact form. Go straight to my email, I always read it. You can voice your questions, concerns, comments, anything you'd like to tell me about the show, suggestions for people to interview for new topics, anything you like. You can also donate to the show there. You can subscribe to our Patreon, where you can download previous bonus episodes that we've released for those who are willing to support the show financially. But if that's not an option for you, if you don't want to do it, the best thing you can do to support us, as always, is to tell as many people as possible to listen to the show, until our army of listeners is strong enough to take over the world. Until then, take care.
Thank you.